Piyush, so 15 seconds.
Yeah. It is like.
It's fine. Okay. Sure, I'll just give a brief introduction. So Varun is a young dynamic researcher. He works on many different directions and uses many different tools and techniques, including in stochastic modeling and optimization, applied probability, algorithm design and analysis, and mechanism design. He's been working generally in the queuing theory space and now lately in learning and control as well. His PhD is from Carnegie Mellon University, and he and I first maintained contact when he was a BTech student in IIT Delhi. So Varun, great to have you here.
Thanks for the invitation. I mean, yeah, as Sandeep was saying, I had a chance to visit TIFR when I was a BTech student, but that didn't happen. So I'm sort of glad to visit virtually and hopefully maybe in June in person.
Yes, yes.
So this talk, I mean, I'll try to keep this sort of a little bit non-technical because I think the audience is slightly broad. So in this project, it's ongoing still, and we're trying to address some questions on how you can use mechanism design for allocation of public goods. And what I mean by public goods here is that you can't use monetary transfers for allocation. So you can't ask people to pay money. So instead we'll use delays as the currency somehow to sort of use for assigning public goods. So one application that you may want to keep in mind is allocation of public housing. So this is something that's at least common in US and some Latin American countries where you have multiple housing projects, and you can think of they may be in different areas of the city, so people may have different preferences over them. And one common design for how allocation of these housing projects to economically disadvantaged people works is through what's called a one-strike multi-queue design. Right. So what's a one-strike multi-queue design? So you have a waiting list for each housing project. So that's the multi-queue part. And tenants may have preferences for which housing projects they like. Right. So when someone enters the system, for example, this person, they can choose to enlist in multiple waiting lists, depending on which one they like. And the matching happens through a first come first serve system. So let's imagine that someone vacated a unit in this sort of blue housing project. So there's an opening. So how does the matching system happen? We just look at the person who's been waiting for the longest for the waiting list for this housing project, and he gets he's offered this unit. Okay, so in the one strike design, this person who's offered the unit may say no, but then he moves to the bottom of the waiting queue. So you can imagine something like a 3-strike design where you can say 3 up to no up to 3 times, and then you'll move to the back of the queue. Okay, so that's one sort of application to keep in mind. Now, the system designer who's designing this matching system may have multiple metrics in mind. For example, they may want some sort of demographic parity, or they may sort of want sort of fairness in different metrics, but at least 2 metrics which are important are delay and match quality. So you don't want people to wait too long to get matched to a unit that they like, and you also would like people to get matched to units that they like. Okay, so if you think of these two sort of trade-offs, then the design that I just showed you, this multi-queue design, is at one extreme where you expect that the match quality would be high because people would only enlist for housing projects that they like. But the delays could potentially be long, right? So maybe some housing projects are oversubscribed and others may have empty units, right? So it's sort of good in one metric of quality, but maybe not as good in delay. And the other extreme intuitively might be what's called a single citywide waitlist, where you just have one waitlist for a common waitlist for all the projects, and then just people join that one waitlist. So you'll get offered whichever unit becomes available. You don't really have a choice of where that is, and you can say no, and then you'll move to the bottom of the queue, right? So that's sort of the other extreme where, because you sort of don't have any control of where you get matched, the match quality may be poor, but at least the delays are balanced because you're pooling the entire capacity of these housing projects. Right? And the goal of this project was to sort of examine this trade-off, like what are possible matching policies or mechanisms, and how does this trade-off between the match quality and the delay materialize. Okay, that's sort of the high-level goal of this project. And the view that we took in this problem is that the system designer takes a very light touch to what the matching policy is. Right, so we basically view the goal of the system designer in this problem as a menu designer. Okay, so what does the system designer or the planner do? So he just offers a menu, which is basically a bundle of wait lists. Right, so what's a wait list here? It's basically a bundle of servers. Right, so for example, this wait list has the blue and the red housing project. Okay, I'll tell you briefly what happens with this menu. Okay, now you can imagine that there are people sort of waiting in these wait lists. So that's these people. And when a new person joins this system, so unlike what I showed you in the first slide, in this view, I can join exactly one wait list. Right? So I can join like one bundle, which basically says that I'm okay with getting matched to any of the housing projects which is served by this wait list. Okay, and I mean, we'll get to this in a bit, but when a user makes this decision, he kind of anticipates what might be my average waiting time if I join this wait list, what might be the likelihood that I get matched to one versus the other housing project. That's part of this wait list, right? So we'll get to that in a bit.
And one waitlist might be a complete subset of the, so the things offered on one of the queues might be a complete subset of.
Exactly. Yeah, exactly. And that will be something I'll also revisit later. So I can have like exactly. So one extreme could be I offer every subset, and the other could be I sort of restrict which subsets people can't join. Right?
So
I offer a.
Mm-hmm. No, are there any other applications also to keep in mind the way this fits in, or?
So I mean, organ transplant is one. The only reason that's sort of trickier is because there's the scoring rule which prioritizes how you even offer units to people. So so that's one. The other is also for like child adoption. There are these kind of waiting lists where if you want to adopt a child, then you sort of join a waiting list. You maybe say that, okay, what might be your preference in terms of age group or something.
Mm.
So those are the three that we have kind of thought of so far.
Okay.
Right. But again, in all of these sort of there are complications like screening and that an issue that we are sort of not modeling here.
Okay.
So okay, so the planner offers this menu. The user sort of then anticipate the delay and the likelihood of getting matched to each of these projects before they join. And then the matching is still first come first serve, right? So if a unit becomes available, let's say in this housing project, then we look at all the waiting lists which are served by this housing project. We see who's been waiting the longest, and then just we serve according to that, right? So that's sort of by a very light touch. So we're not actively prioritizing people, we just sort of offering these menus so that it's also easy for people to sort of understand how the matching will happen. We just tell them, okay, you wait, and then you'll be offered units in a first come first serve manner. And it's also somehow temporarily fair. Like if you arrive into the system before me and we're kind of waiting on the same unit, it's not fair if I get served before you, right? So for those reasons, we're sort of assuming that the matching policy is fixed and it's first come first serve. Okay. And the key idea is that by controlling what menu is offered, the system designer can somehow maybe optimize the trade-off between delay and match quality. Okay. And before I sort of go into the formal model and the results, let me sort of say two things that I think are important for applications which we are not modeling. So we will not model this sort of one strike or three strike design. So we will assume that if you offer a unit to a user, he's forced to accept it. And we will also not model users abandoning the system. So for example, in organ transplant, the demand outstrips the supply. So there are people who will wait and eventually they'll just die and abandon the system. So we'll assume that's not the case here. So the demand will always be less than the capacity. Okay. So that's sort of the high level picture. And now I'll jump into the model in the next slide. So I guess any questions before that? So here's the formal model. So this is a little bit of a busy slide. So I'll go through this slowly, but feel free to step in and ask questions at any point of time. So the primitives of the model include servers. So servers now correspond to the housing projects, right? So I'll have some servers, and new J will represent the capacity of the server J. And you should just think of that as the rate at which units of type J become available for matching. And we'll assume that's a Poisson process. At the other end, we have customers, and customers have multiple types. So it's a heterogeneous system. What will be important are these rewards. So V theta J is the reward that a type theta customer gets if he gets matched to a server of type J. And alpha J will just be the arrival rate of type J customers, alpha theta, sorry. And again, that's a Poisson process. So those are all the primitives of the system. Knowing these primitives, the system designer then offers this menu, right? Again, like bundle of servers. And now the customers decide their strategies. Okay, so now the strategy of a customer is denoted by these probabilities Q theta J, Q theta I, sorry, which says that what's the likelihood that a type theta customer joins a type I waitlist. Okay, and I'll assume here that the queues are unobservable. So when a customer makes this decision, they anticipate the expected delays, but they don't really know what's the current length of each queue. Again, I'll say maybe something towards the end of this talk on this assumption. But for now, for simplicity, we'll assume we sort of ex ante anticipate the delays and the probabilities of matching. Okay. So once customers pick their randomized strategies, there'll be some aggregate arrival rates into each of these service classes. We'll call them lambda sub I. And the outcomes which will be important as a function of these arrival rates would be the average delay for each service class, W sub I, and also the probability of matching, right? So if I join a service class of type I, what's the likelihood that I get matched to a server that's served by this waitlist? Okay. Sandeep, you have a question?
Yeah, so why would you not eventually get matched? I missed that, I guess.
No, you'll get matched, but you don't know which server you'll get matched to. So that's probabilistic.
Oh, yeah.
So you will sort of think of that while you're making your decision.
Okay. All right.
Yeah. So the sum of Pij's over J would be 1. Yeah.
Mm-hmm.
Okay. Yeah. So that's the model. Questions before on any part of this model?
So there's no limited resources. So all the resources do, like, there's a constant rate at which all of them are becoming available. It's not like at a certain time a certain resource.
That's exactly, yeah. So we have to, this Poisson assumption is kind of critical, which in some applications it's fine. Like I think an organ transplant, definitely, I think that's fair. In housing allocation, it's unclear. Maybe there's seasonality effects and so on. But I guess maybe if you look at like a long enough time scale, like compared to how long people wait, if the arrival process is sort of still almost stationary, maybe that's still a reasonable assumption. Good question, yeah. Okay. Good. So that's the model. And now we get to sort of how do we define the equilibrium? So what do customers care about when they're making their decision? So they are looking to maximize their utility, right? So this U theta I is the utility that a type theta customer gets if he joins service class I when everyone else is following a strategy queue, right? So what's that? It's a combination of the match value that I get. So this basically just says that if I join service class I, then I'll get served by server J with this probability Pij. I get this value V theta J from that server. So that's my average match value minus some delay disutility parameter delta times the average waiting time of service class I. Right? So delta controls how sensitive I am to delay versus match value. And we'll assume delta is common across all the types. Okay, so that's my utility. And then what's equilibrium? So we'll say that this set of strategies Q is an equilibrium if the following is true, that if under this Q, some type theta joins this waitlist I with non-zero probability, then I must get at least as high a utility from this service class I than from any other service class. So that's what it means that for Q to be in equilibrium. So that's the game from the side of the customers or the users. Okay. Any questions so far? I mean, I know this will take a little bit of, I mean, it's not hard, it just takes a little bit time to get used to symbols and so on. Okay. So that's
all the utilities actually are equal. So the equilibrium condition implies, for example, that all the queues that so in the equilibrium, all of those utilities will actually be either zero or equal. So that's really what I mean.
They will be.
No, so all the ones where it is, all the ones where QI is positive will be equal.
Exactly. And that will be, yeah, that will again be crucial to pin down the equilibrium. So some of them are equal, others are strictly below. Okay, so that's the game. Now, what does the social planner care about? The one who's designing the menu. So they also care about some combination of the average value and the average delay, right? So here, this V bar is basically just the average value across all users. Don't focus too much on the formula, just the average value, right? And this W bar is just the average delay across all users. But the social planner may weigh these two differently than the users, right? If zeta equals delta, then I'm maximizing welfare. But if zeta is higher, then I care more about minimizing delays. If zeta is less than delta, then I care more about maximizing the match value, right? So he wants to maximize this subject to the fact that Q star is an equilibrium. So there's one sort of messiness which I'm doesn't maybe come out through this, which is somehow I'm jointly maximizing the menu as well as the equilibrium. So we don't yet know what happens if I have multiple equilibria. We assume in this formulation that if there are multiple equilibria, then I, as a planner, somehow can choose the most optimistic one for my objective. So that's like one issue which we haven't sort of dealt with. What menus do have unique equilibria and so on. And again, that will something I'll mention at the end of this.
Sorry, Varun, so the social planner has this menu under their control. So exactly what does that mean? What can they do?
So they can optimize the menu, and for that menu, pick the most optimistic equilibrium, and then that's jointly optimize over both of them.
Okay.
Yeah. So this is something that, I mean, these two are something I optimize over. Okay. So just sort of to give you a picture. So this is an example with 5 customer types and 7 examples. So this x-axis is the matching reward, y-axis is the delay. And what we did here is I'm just like randomly sampled some menus and found the equilibrium for those menus, right? So each of these dot is a possible menu I could have chosen. And you see the trade-off here in some sense, right? So the ideal case would be that we have a high match value and a low delay. So we kind of want to be somewhere here, but instead we have this sort of this trade-off between delay and reward. And our goal is ideally to sort of explore this frontier and see how can we find menus which are on this frontier or maybe close to it. Okay, so that's sort of the objective. So providing some analytical insights into what good menus are. And the second main objective is to maybe find a computational approach to generating good menus. So solving this. Okay. Good. So what I'll do in most of my talk is just for insights, I'll focus on the case of 2 servers because they'll be able to sort of pin down exactly what all the menus are and what's the trade-off. And towards the end, I'll come to this question of this computational approach of generating good menus by expressing some menu design problem as a mixed integer linear program. Okay, so that sort of is the direction that we'll head towards. And for this 2 server problem, I'll just in the rest of this talk, I'll focus on this simple example. I have 2 servers with capacity 1, and I just have 2 customer types. Okay, and because I just have 2 servers, we can roughly summarize the preferences of the users by the difference in the value for server 1 versus server 2. So the absolute values don't matter that much. What I care about are the difference in values. Right, so here my type 1 customer strongly prefers server 1 he has 10 units more value from server 1 than server 2. And the second customer type strongly prefers server 2. Okay. Also, more importantly, server 2 demand exceeds server 2. So that will sort of help simplify some of the menus that we look at. Okay. So that's the example we'll be using in the rest of the talk. And before I jump into the menu design question, the first question that one has to ask is, okay, what is a good benchmark, right? So that we can sort of say, okay, this menu looks good or this menu looks bad, right? So we sort of look at a very optimistic benchmark where we optimize the reward and the delay separately, which is what we'll call the first best, right? So if I just want to maximize the matching value, a naive upper bound is I just solve a max flow LP, right? So if I could directly control the flow from a customer type to a server, F theta J, I could just directly maximize that value, and I can write that as an LP where I serve all the demand for each customer type. I don't serve more demand than the capacity of a server, and just maximize this value. So that's one end where I'm maximizing value. The other extreme is if I just want to minimize delay, what could I do? I can just view, instead of having these multiple servers, multiple customer types, just pool everything into one server and one customer type, right? So this is essentially a queue where I have Poisson arrivals with a Poisson capacity with rate 2, Poisson arrivals with a demand of 1.5, and like a standard queuing theory result says that the average delay is 1 over the capacity minus the demand, which in this case is just 2. Okay. So this is basically all the queuing theory I'll need in use in this slide, in this talk, just this formula. Right, so that's my first best. And now we can at least start comparing or placing menus on this frontier, like how are they compared to the first best in terms of delay and reward. Any questions or because I don't know like how much people are exposed to queuing theory, so I wasn't sort of clear if this is fine. Okay, so now we can jump into the menu design question. So remember, a menu was a subset of servers, right? So in this case, since we have 2 servers, there are only some subsets which I can offer. So there's like one for each queue and one which is from the joint bundle, right? So if those are the bundles I can offer, there are only few menus I can offer. One menu I can offer is this full menu. This is what we saw in the first slide, where I can either join a waitlist for server 1 alone, one waitlist which is for server 2 alone, or I can sort of enlist in both server 1 and 2, which is this joint queue. So that's what we call the full menu. Or I could join this other extreme, which was the single line, which essentially I have no option. Or we can come up with these menus where you are forced to join either server 1 or server 2, but you can't multiple enlist. That's what we'll call the dedicated menu. N1 is where there's a dedicated for 2, but then there's also a bundle which is joint, and then the flip one. Okay, so these are the only 5 menus that we can offer where I'm stable, right? Because you have to use the capacity of both servers, otherwise you cannot serve the demand. Okay. So we'll start with analyzing the simplest menu here, which is the single line menu, just for intuition. And we'll gradually sort of look at my sort of fancier menus. All right, so if I want to find the equilibrium for the single line menu, essentially I don't really have any choice, right? Because there is no sort of non-trivial strategy. I just have to join this one bundle that I offered. And therefore, at least in terms of delay, this is exactly the same as the delay of the first best that we saw, right? I just have single queue, so same delay as first best. But what can I say about the matching probabilities? Because that also matters, right? For the match value. So essentially what you can think is, okay, imagine the guy who's at the head of this queue. What's the probability that he gets matched to server 1 versus server 2? My arrivals are Poisson, so each of them is likely to be the first that arrives. So my matching probability in this case would just be proportional to mu's, which would be half in this case. Okay. So this is not good from the point of view of matching, because I have these 2 customers, they have very different preferences for these 2 servers, but they're equally likely to get matched to either of them. So what we can prove is the following, that the single line menu attains the minimum mean delay. So this is sort of not hard. This is sort of standard queuing result. But what's interesting is that it actually achieves the minimum matching reward among all possible menus that you can offer under equilibrium. So this was a little bit surprising, but it's true. So now we can place it on this frontier where it has the same delay as the first best, but has extremely poor reward. In fact, it's the complete extreme. It's sort of best in one, the worst in the other. Okay, so this was the easy menu. Questions on the single line menu? Okay. So now let's sort of look at a slightly fancier menu, which is this dedicated, where I have a single dedicated waitlist for each of these servers. Okay. So this is a little bit tricky, but not very hard, right? So how can we think of the equilibrium? So let's imagine that under some equilibrium strategy, there is an arrival rate lambda1 and lambda2 to these wait lists, and waiting time which is W1 and W2. So let's walk through the analysis a little bit slowly. So can it happen that my waiting time for waitlist 2 is less than or equal to my waiting time for waitlist 1? Could it happen in an equilibrium? So it cannot happen. Why? Because type 2 customers strictly prefer server 2 or waitlist 2, right? And now if their delay is also less than server 1, everyone will want to join waitlist 2. And that doesn't have enough capacity. So this cannot happen. So what should happen in equilibrium is that my waiting time in waitlist 2 has to be bigger than waitlist 1. Okay. Now what will happen? So all the customers of type 1 will strictly prefer waitlist 1. It has a lower delay as well as they prefer the value. So all of them will go there. But now the type 2 customers have to randomize, right? And as Piyush was saying, if I have to randomize, I must get the same utility from each of them. Okay, so for now, actually assume delta is 1. I sort of forgot to mention that. So my, what happened to my pen? 1 second. Pen has stopped working. Let me pause my slideshow and then just restart.
Oh,
My style stopped working somehow.
Your cursor moving?
Yeah, but somehow it doesn't write when I try to write.
Okay.
Yeah. Let's see. I can't even stop my slideshow. That's interesting.
so should he log in and log out?
No. You can hear me, right?
Yeah, we can hear you. Yeah.
Okay. I think my PowerPoint has frozen. So let me just restart my PowerPoint. In the meantime, you can analyze the equilibrium.
Well, it's simple, right? I guess. So the second stream will divide itself in such a way that it's the right proportion, so the cost is the same both ways.
Right.
But you always achieve that, basically. Yeah.
That's right. So yeah, that's exactly what Piyush was saying, right? So that comes to our SQ.
Right.
Right. And you can see the screen still.
Yeah. Yeah, you're moving.
I hope I can also try. Good, I see. So, all right, I can write. Good, so exactly. So what would happen? So we concluded that my waiting time has to be bigger than waiting time of 1, and I was going to say delta is 1, right? So therefore, I must also have this equals 10. So we have two equations now, right? So my waiting time in 1 is, as we saw earlier, it's like this mu1 minus lambda 1, which I can write instead as saying that mu1 minus or rather mu j minus lambda j equals 1 over wj. That's one set of equations. The other set of equations just says w2 minus w1 is 10, and I can solve for the equilibrium. Okay. So it will be somewhere here. So the delay performance is not as good as single line because I'm not pooling my capacity, but it should be better in terms of value because at least type 1 customers are getting their preferred server. Type 2 somehow I have to mix, but still better than single line, right? So somehow that's what's happening to my front here. Okay. So those were the easy menus, and now we get to the messy menus where somehow I have to sort of look at non-trivial interactions among waitlists and servers. So let's look at the N1 menu first as one example. And the first question is, okay, how do we even analyze the steady state if I give you the strategies for all the users? Okay. Now, this is an extremely messy problem, and there's a very elegant result of Ivo Adan and Gideon Weiss from 2014, which gives the exact analysis of this queuing system. I don't expect you to read any of this, right? I just want to sort of get across the fact that this is extremely messy. And what it involves is that you have to enumerate all the permutations of your servers, right? So you could still do it for 2 servers. It's still messy, but it becomes very highly interactable as you sort of go beyond that. And optimizing menu on top of that is sort of infeasible. So what we do is this common trick that we queuing theorists use, which is we resort to a heavy traffic analysis, which is like a queuing theorist's central limit theorem, if you will, right? So what's happening in my heavy traffic scaling? So this is the same slide as before. What I've done is I've just added a superscript of epsilon to all the parameters. And really what's happening is that in my epsilonth system, so I have these sequence of systems indexed by epsilon, I changed the arrival rate of the customers, and I changed it in such a way that I approach a limiting arrival rate capital A theta as my epsilon goes to 0, where my capital A theta are chosen so that in the limit, the total demand equals the total capacity. And I approach it from below. So that's what we mean by heavy traffic as epsilon goes to 0. Okay. So that's really all that's happening when I move to heavy traffic. I have to change my customer utility a little bit. And the only thing that's happening here is that I'm also scaling my delay disability. So remember, I showed you this formula for delay. It was 1 over capacity minus demand. So as epsilon goes to 0, that will increase as 1 over epsilon. And to keep my problem non-degenerate, I should also therefore scale how much weight I put on delay, so that I approach some limit. So that's all that we're doing here.
Varun, could you have kept the overall arrival rates equal to overall service rates and done some kind of fluid analysis?
I think the delay will get fixed there. So I want the delays to also emerge. I think you'll still get non-trivial matching probabilities, but the delays will somehow get stuck. Yeah. But yeah, I haven't thought more on that, but that'd be interesting. Okay.
Yeah, that might just be a very simple problem.
Right. Yeah. Okay. So yeah, and because I'm sort of also scaling both the epsilon and the delay, we'll use this hearted W to denote the limiting waiting time, just limiting scale waiting times, and that will sort of be important instead of just the overall waiting time. So that's really all that's happening in heavy traffic. And before I move to N1 menu, let me actually revisit this dedicated menu that we looked earlier and tell you what's happening for this in the limit. And the only thing that I'll say, which is maybe only interesting to queuing theorists, is that when you look at the equilibrium, there is a limiting value to these probabilities, which matters and which we could have guessed from what we saw earlier. But there is also a direction along which you approach this limit, and that matters this time because that determines what the waiting times are. So that's maybe something that's sort of only of interest to queuing theorists. Okay, so that's what's happening for the dedicated menu. But now we can actually say more than what we said earlier in heavy traffic. So we can actually prove in heavy traffic that the dedicated menu actually attains the maximum matching value. So earlier we saw it's better than single line, but it's actually optimal. And the proof, I won't go through the proof because I'm running short on time. It kind of just shows that if I give you any equilibrium for the dedicated menu, that can be used to define a dual variable for my max flow linear program, which satisfies approximately complementary slackness. The approximation is like this epsilon. So it's also sort of approximately value maximizing is what we mean. Okay. Good. So that's what we can say about the dedicated. So I kind of move the dedicated menus dot so that it aligns with the first best. We can say something more. We can also say that if I offer any menu which has dedicated as a sub menu, so I offer one waitlist for each server, but I have other bundles also. So dedicated plus something else, all of those menus will actually maximize value. So there are multiple menus which maximize value. The delay analysis kind of becomes tricky, but I'll come to this in a little bit, that all of these menus somehow don't have good delay performance. So if you somehow insist on getting maximum value through these, you'll kind of suffer in delay. So that's like one takeaway, going back to Piyush's initial question, which is if you kind of care about delay, you can't just let people join any subset of the menus you've offered, because then they'll want to join the queues which are sort of dedicated, and then you'll get just poor delay performance. So you kind of maybe want to restrict choice if you care about low delays. So that's like one takeaway from this. Okay, so that was the dedicated menu. But now let's go back to the N1 menu, which was the reason we introduced this heavy traffic limit. Okay, so here I have like one bundle of servers 1 and 2, and then one dedicated for server 2. Okay. And let's sort of quickly go through the equilibrium analysis for this. So one thing that comes out of the equilibrium analysis is that if there was any sort of flow on this arc, which I have shown as a dashed, if there was sort of non-negligible flow on this arc, by non-negligible, I mean something that's order 1, not order epsilon. If that was the case, then I would actually get the waiting times of these two service classes being equal. Right? Why? Because in some senses, server class 2 or server 2 is serving both of these wait lists, and it's doing first come first serve. So it's sort of trying to equalize the waiting time of it's trying to equalize the waiting time of the guys who's at the head of the queue. Right? So let's imagine this guy and this guy, who is kind of equalizing the delay of these two. So the waiting times will be equal. But that cannot be sustained in equilibrium for the same reason that we saw earlier, because then all the type 2 customers want to join waitlist 2. Right? So you must, as before, have the difference in waiting times equals the difference in this value. But now what we can show is that because we have added this sort of small arc, even though it has negligible flow, it actually lowers the delay of class 1 waitlist. There is some pooling that happens. Earlier, if I was just looking at the dedicated menu, the waiting time of 1 would be 0.529, 0.5249. So I gain something by adding this arc, even though there is no flow in the limit. Okay. So that's basically what happens to the N1. So you kind of have the same optimal reward as dedicated, but you lower the delay. And that's sort of another takeaway of this menu design problem, which is if you want to improve delay, you can just chain the servers. What do I mean by chaining? So imagine that I had like 3 servers. And if I offer a dedicated menu, then I get a waiting times W1, W2, W3, where this was the ordering. let's say like 3 had a higher delay than 2 than 1. So, and this was my dedicated. If you just add these arcs where you sort of chain them in the order of the delays, you'll get the same reward as the dedicated, but you just lower the delay because there is some pooling that happens. So that's what this chaining means. Chaining does. Now, one thing again, which maybe I can briefly mention, is that in all of this, I was saying that we assume that the queues are not observable. If you make the queues observable, then you get chaining without doing chaining. So you can just offer the dedicated menu, but people sort of, because they can join, they can look at the queues before they make their joining decision, they'll do the pooling for you. And it acts like a chain system, even though you are not doing the chaining. Okay, so that's sort of just one aside. So even though we made the non-observability assumption because of simplicity, it's sort of not that restrictive. Okay. So that was the N1 menu. The N2 menu is kind of simple, because for the N2 menu, you can actually see that W1 equal to W2 is feasible in equilibrium, right? So what will happen in this case, type 1 customers strictly prefer waitlist 1, all of them will go there. Type 2 customers all prefer waitlist 2, all of them will go there. And you get perfect pooling. And in this case, you also get the optimal value, right? Because all the type 1 customers go here and they kind of occupy some capacity of server 1. And whatever is remaining gets taken by the customers of type 2. So in this case, you can actually get the optimal delay and the optimal match value, but this is not always possible in all with all primitives. Thank you. So this sort of is the complete picture for what happens for the example that I showed you early on. And just to recap, this is what the typical frontier would look like with 2 servers, right? And just to recap, what we saw is that you can have a value maximizing menu where dedicated always maximizes the value, but also has a pretty bad delay. And for 2 servers, it has the highest delay. It's not true for general number of servers. You can actually have even higher delays. Okay, but you can improve the delays by chaining. What we saw was that if you offer dedicated as a sub menu, then again, you get the maximum match value. And one takeaway from what we've seen so far is that you want to restrict choice if you want to get good delay performance. Right, so those are value maximizing menus, or we could have delay minimizing menus. And again, we saw that single line minimizes delay. You can sometimes improve it by, like in this case, for example, N2 would improve the delay, but not always. So this is a qualitative picture of what happens with 2 servers. Just to give you one quantitative result for what does this picture look like, let me give you look at one sort of example where we'll see what is the trade-off between value and delay, right? So let's call this gap, which is the difference between the best value you can get and the best value that you can get if you insist on minimum delay. So we call it cost of delay optimality. So you're insisting on delay optimality. What do you lose in value? And similarly, this vertical thing is what we call cost of value optimality. If you insist on maximum matching value, how much do you lose in delay distributility? And we want to see how do they compare, which one is cheaper in some sense. So the theorem is the following, that so imagine that now I have a continuum of users, and if I look at the distribution of the difference in their values for the 2 servers, that is a uniform distribution with some support between L and U, right? I'm not saying what in L and U are, they could be arbitrary. So for example, if I have both L and U are positive, then I'm saying that everyone prefers server 1. Or what could happen is that my L is negative and U is positive, then some people prefer server 1, some people prefer server 2. It doesn't matter what that is, as long as it's uniform. The cost of reward optimality is twice of the cost of delay optimality. So this vertical thing is twice of this horizontal. So somehow it's more expensive to insist on optimal match value. Okay. At least in this example, but we've seen it sort of more generally in our experiments. And we're sort of still trying to pin down this result more generally. Okay.
With two servers.
With two servers, exactly. And the sort of uniform distribution for the different.
So does the two, so where is the two coming from? Is it a property of the distribution or of this, there being two servers?
This I think is because of, uniform distribution. So the if this distribution was not uniform, it won't be two. If it wasn't two servers, then I couldn't even sort of have a single parameter to sort of quantify the valuations. I'll sort of need a bit more. Yeah.
Sorry, Varun, what's the welfare solution in this picture?
So you can actually, welfare maximizing, it will depend on the delta value. It could either be this or this, depending on which one users prefer.
Right. Okay.
Yeah.
I mean, so it's no better than what you get through this kind of gaming amongst people.
Oh, I see. Oh no, so you can get the
social
first best.
Yeah.
So you can get the first best. So if you can direct people to where they can go, you can actually get the first best.
Okay. Or you can get the first way. I see. Okay.
That's it. Yeah.
Right. That's what you're comparing to.
That's right.
So somehow you've not been able to come to first best through all of this. Can you come? Do you look at the ratios with the first best and say something, or?
So the thing that makes it hard is because we have difference in reward and waiting time. The things could, okay. I think with these differences, it becomes very hard.
Yeah.
We can maybe say individually for the value and individually for the delay, but not for the welfare. But we can, we should look more into those things. So I'm almost out of time. So let me just quickly say what we can do beyond two servers. So beyond two servers, we don't really have very nice results other than the generalizations which I sort of mentioned. And so there our goal is to be able to write like optimization formulations of menu design, right? So mixed integer linear programs, for example. And so far we can only do it for some classes of menus, some subclasses of menus. One which I think seems sort of the most maybe flexible are what we call partition menus, right? So here what you do is you sort of first partition your servers into bundles. You have a dedicated waitlist for each of these bundles, and then you just chain them as we chain the dedicated menus, right? So, the reason they're kind of nice is because you've kind of already seen two examples of these partition menus. So single line basically just bundles all the servers into one and offers a wait list. The dedicated basically just has each server in its own partition, and I have a dedicated wait list, and then I chain them. And these are like two extremes on this frontier. And the hope is that maybe if we sort of have more other partition menus, maybe you can sort of get some sort of frontier along this. So we can actually write optimization within partition menus as a mixed integer linear program. The other kind of menus that we can also write as a mixed integer program is what we call tailored menus. So in some sense, what's happening here is that, I guess if you know, like these direct revelation mechanism, it's kind of that philosophy where I will basically create a waitlist specifically tailored for each customer type. And if everyone just joined this waitlist that I told you, it will be in equilibrium. That's what we mean by a tailored menu. So we can also sort of optimize within these menus. And something which we call an optimal reward menu, but let's not worry about it. Let me just quickly jump to the results, the experimental results. So here I'm showing you the numerical results for a 4x4 system. So 4 customer types, 4 servers. And I'm picking the valuation distribution as the type of the customer times the type of the server. So theta is 1, 2, 3, or 4. J is 1, 2, 3, or 4. And essentially what we're saying here is that everyone kind of prefers the same servers, but there are some people who get more out of joining this most preferred server. Right? So everyone prefers J equal to 4 server, but if I'm a type 4 customer, I somehow get more value. So in a welfare maximizing solution, I should get matched there, right? Plus some noise. So what we can see here is, so this black line is the single line menu, this other black square is the dedicated menu, and the partition menus do actually give you some sort of frontier along this line. Okay. And this red is the tailored menu where we somehow want to minimize delay and we tell everyone which menu they can go to. Okay, so this is something that we get some trade-off. But I now have the same example. I just increase the noise in my valuations. So I still have this theta times J value, but I just make it like slightly noisier. And again, I do get some frontier using partition menus, but I can actually get very close to the first best using this tailored menu. So if I can sort of design a menu where everyone sort of goes to their classes, I get optimal delay, almost optimal matching value. Okay. And this basically sort of gives at least some empirical evidence that there is a trade-off, but for certain kind of valuation distributions. And it goes away if you make these valuations uncorrelated across customer types. Or you can imagine settings where I have like spatial preferences. So I want to go to a hospital that's close to me, where it's actually negatively correlated. And again, the frontier will almost disappear and you can maybe get very close to the first best. Okay. And this is similar to, I guess, if you know of these results on these stable matching algorithms, right? So there are these results which say that, okay, if I have a stable matching problem between like men and women, where the ranking of women that men have are generated uniformly at random for every person, I can find a stable matching algorithm where everyone gets like within like log n of their top preferences. It's kind of similar, where if I have a lot of independence in people's preferences, I can pretty much get first best. That's what's happening here also. But we don't have, again, like a nice theoretical result like these stable matching results. Okay. So this is kind of the end. So let me just sort of mention some concluding remarks. So, I mean, this is still, I think, we're just barely scratching the surface of this problem. We have some nice analytical results. For example, that if you want to improve delay performance, then you kind of want to restrict choice. It's a bit like a Bayes paradox kind of a result. But I think many important open questions, right? So one is this question of what are the menus for which we can at least even say that equilibrium is unique. Right now we're having this sort of equilibrium selection problem that we are solving optimistically. I think other sort of notions of fairness across customer types is also important. Right now we just have this temporal fairness notion, but maybe you want the utility of each customer type to be sort of also balanced. I think these overloaded matching systems and these case-like assignment, like where you can say no, are important if you want to go into like these organ donation kind of organ matching application. I think those also seem interesting. And I think there, I think these fluid models are actually more useful for overloaded matching systems. Good. Okay, so that's where I'll stop. Thank you.
Thank you. So, if there's any questions? Varun, can you just give, can at an intuitive level, why did restricting choice of servers helped in delay performance? Can you just spell that out a little bit more? I missed it. Yeah.
So I mean, okay, so the intuition I have is basically just from this result. I mean, in some sense, what's happening is that if you offer a dedicated plus menu, and again, you look at any equilibrium, you again get this result that this defines a dual solution, which is almost complementary slack. Right? So that at least gives you the proof for why this is value maximizing. In terms of, I think, why delay suffers, it's I think my intuition is just this, which is somehow it's unclear. I mean, I kind of have to open up this calculation, and I don't think there's a intuition other than this.
Okay. Okay. That's very nice.
Yeah. And again, I mean, because there are examples where this doesn't happen, right? So for example, in this two server example that I showed you, you could actually do both with this N2 menu. So it's not always true, which is again, I think there's no universal answer. Sorry, I don't have a good answer. Yeah. I mean, this fluid, I mean, going at you, this question of the fluid problem. So that also we looked at for a different problem where we don't even have a game theoretic notion. So you can actually tell people where to go. And it became even APX hard for us to find good menus because you can kind of reduce it to like 3-dimensional matching. Even if people have 0-1 preferences, even that became like a 3-dimensional matching. So there is some sort of hardness there. But even we're writing MIP here also, so it's not like we're getting away from it. But these things become hard rapidly.
Okay, so if there are no more questions, we are right on time.